Good morning, everyone. My name is Leader. Today, we will walk through the evolution of contact lens materials, shifting from bulk material adjustments to advanced surface and smart interface modifications. The timeline begins in 1960 with traditional hydrogels. The theoretical foundation of these materials relies on swelling theory, balancing the entropy of mixing with elastic free energy. To achieve higher oxygen permeability, developers tried creating ultra-high water content structures by lowering crosslink density to form a loose molecular network. However, this led to a major physical limit, localized stress concentration, which resulted in material fracture. This brought the industry to a critical question: is high water content truly the answer to high oxygen permeability? The physics presented a strict ceiling. The theoretical maximum oxygen permeability (aka of pure water is only 80, while commercial hydrogels typically ranged between 20 and 40. Furthermore, water content is inversely proportional to mechanical strength. Clinically, high water lenses created a severe pain point. They caused rapid water evaporation, which forced the lens to absorb tears directly from the patient's eyes, leading to dry eye symptoms. In 1999, a new challenger emerged: silicone hydrogels. The integration of silicon altered the mechanism entirely because pure silicone, PDMS, possesses a decay greater than 600 bar. Oxygen transport became independent of water molecules. However, this introduced a new dilemma. Silicone is highly hydrophobic, causing phase separation that led to lens opacity and severe surface fouling. To resolve this, block copolymerization was introduced as a technological breakthrough, restricting phase separation strictly to the nanoscale to keep the lenses optically clear. By 2026, the industry transitioned from uniform material blending to highly sophisticated surface and bulk differentiation, notably through water gradient technology. This architecture utilizes a dual-zone sandwich structure. At the core sits a low-water silicone polymer optimized for maximum oxygen permeability. This core is enveloped by a high-water hydrophilic polymer shell. This design creates an interface that transitions from a highly permeable interior to a highly wettable, fluid-like surface that minimizes friction against the cornea. Simultaneously, current progress has expanded beyond standard synthetic polymers into biomimetic coatings. By integrating polysaccharides, specifically through the covalent cross-linking of hyaluronic acid, HA, directly into the polymer network, the lens surface actively mimics the ocular mucin layer. This macromolecular network locks in free water molecules permanently and inhibits protein denaturation, maintaining long-term surface biocompatibility and reducing inflammatory fouling. Looking toward 2030 and beyond, the field is moving into active smart interfaces. The first upcoming milestone is self-healing materials based on dynamic covalent bonds. Driven by reversible condensation principles, these materials allow free chain diffusion at room temperature for autonomous healing, offering scratch resistance and enhanced corneal protection. Ultimately, the future lies in intelligent, responsive networks. The first one is dynamic network sensing. These interfaces are engineered to bind specific target biomarkers in the tear film, triggering microscopic phase transitions or controlled polymer swelling to enable the continuous, real-time monitoring of glucose levels and intraocular pressure. The second one, which is also worth noticing, is stimuli-responsive drug delivery. By actively sensing microenvironmental variations on the ocular surface, such as subtle shifts in pH or local temperature, the network dynamically modulates its own crosslink density to execute the automated, sustained release of therapeutic drugs. In conclusion, the trajectory of contact lens materials shows a clear shift from simple water-dependent oxygenation to complex nanoscale structures, and finally to active, environment-sensing smart interfaces. Thanks for watching. Feel free to give me a like button. See you next time.